title is Root torsion in higher dimensions.
Okay, thanks for giving me the opportunity to speak here, and thank you for inviting me for 2 weeks. Like announced, I will talk about the root torsion in higher dimensions. This is the article with I think myself and Chris Wendell, and it might be possible that you already heard about these talks. Anyway, I do think. So before talking about higher dimensions, I will try to explain what main properties of contact manifolds in dimension 3 are. So I start with this situation in dimension 3. And I think I hope this might be interesting, even if you don't want to do higher dimensions. I hope this might be interesting because when you try to generalize from dimension 3 to dimension higher, you need to really understand what are important data in dimension 3 that carry properties that you want to see in higher dimensions. So what do we have in dimension 3? We firstly have over-twisted contact manifold. So what this is, M side is over-twisted if it contains an over-twisted disk. If it contains an embedding of a disk of, so you take E2 embedded into M3, and so what do we need? We need, so the disk has dimension 2, the contact structure has dimension 2, we have a free manifold, and if you intersect both structures, like the tension space of D2 and the Xi, we obtain a foliation. So D2 is foliated by Xi like this. So this is the standard picture of the over-twisted disk. And this picture is totally equivalent to another picture, which is just the radial picture, which I prefer for technical reasons. And what does it mean? It means that, so here's a singular point, singularity of the foliation. And the whole boundary is also singular. Okay, so the whole boundary are singularities of the foliation. And if you have this image, you can just perturb it into this one, and you can go both ways, so they're completely good both pictures. And how do they appear, these over-twisted disks? Like, as you probably know, you have a construction which is called Lutz twist. And the Lutz twist consists in introducing a Lutz tube, and the Lutz tube is a contact manifold which is open, which is a solid torus, with the contact structure given like this. This is the kernel of cosine pi r dz plus r sine pi r d phi. So this is C here, and this is r d phi. Okay? And so it's a closed solid torus. And the way to see it topologically is like this. So this is the z-axis, and when you look at the contact structure here, you see that on the central core it's horizontal. So here it's like this. And as you move out from the center towards the boundary, it starts to rotate. So here it's pointing upwards, and on the boundary it's pointing downwards. And from here to here it does a half twist. And everything is symmetric. Okay? And if you have this, then it is clearly over-twisted. So a manifold containing a Lutz tube is over-twisted. And why is this? Because simply you take any slice like this, and this will be an over-twisted disk in this shape. See? So Lutz tube is over-twisted. And for more difficult reasons, if a manifold is over-twisted, it also contains a loose tube. So both notions are equivalent. And but to go from here to there is much harder. Or maybe, whatever. So this was the first property, which is over-twisted or loose tube. Both are equivalent. The second property I would like to explain here is root torsion. So what is this? Probably you already also know. So before saying what it is, I wanted to say if MC and M3 over-twisted, then it has positive root torsion. So in some way, this is a more subtle notion anyway. So over-twisted implies root torsion. And what is root torsion? So to say what it is, I first introduce the half torsion domain. A half torsion domain is a thickened torus, which looks like this. I take an interval 0, 1 times T2 with coordinates R, X, and Y. And the contact structure here, so psi is given by sine pi r dx plus cosine pi r dy. And if I try to sketch this, so this is a typical way to sketch it. It's like this. You take a cube, you identify some of the faces. So this is the r direction, let's say. This is x direction, and this is y direction. And what does it mean? So the x and y direction are the torus directions. So it means that I'm gluing the front side to the back side, and I'm identifying the top side to the bottom side. And as you see, the r direction is always tends to the contact structure. And what actually happens is that on the back face of this cube, of this thickened torus, the contact structure is horizontal because the sine term vanishes, and on the other side, on the front, on this side here, it's also horizontal. Looks like this. And if I take whatever line R, like this, what I will have is that it also does half a twist. So here, let's say the red field points upwards like this, and here will point downward like this, and this happens everywhere. Whatever line R I choose, I mean, this is all x and y invariant. Okay, so the contact structure of this block, which is a half torsion domain, is just like this. You start on this wall and you do half a twist to this wall, and everything goes parallel. Okay, and this is a half torsion domain, but we are all interested in positive torsion. Positive torsion means this. So this is the definition if you want. As positive root torsion. If it contains two half torsion domains glued along one face or on it's two blocks like this. So one block and then the next one. So it contains this thing, 0 times 2. I'm just shifting here. Times C2 with the same context structure, given my kernel of cosine of sine pi r dx plus cosine pi r d. Okay, so if I do the same picture, I will just obtain a longer domain like this. I have the same identification on these faces. And what happens is that on this side, it's on this side, the context structure is horizontal on this side, it's horizontal on the end, and it's horizontal on the central torsion. Okay? So as you move from that side to that side, you do full turn. And for reasons that for now may seem a bit mysterious, this is not so important. This, I mean, if you want to have positive root torsion, the notions have been defined to make sense. So this is the thing that really distinguishes some contact manifolds from others. You have at least two blocks like this. Okay. Okay. So I would like to generalize this somehow to higher dimensions. And before I really, I can, since I don't know what properties these things have, I could generalize whatever way I wanted to. My way to generalize is that both of these properties imply certain fitability properties, and I would like to find similar sets in higher dimensions that imply the same fitability properties for higher dimensions. Okay. So my criterion, whether my generalization or our generalization works or not, is that it implies similar fitability properties. I'm saying this because over-twisted, for example, has a very implies flexibility, but we are far from doing this in higher dimensions for now. Okay, so I just write the main criteria to see whether the generalization works. There are theorems. The first theorem is if m psi over-twisted, then not weakly fitable. And the other one is if m has positive root torsion, do you hear me? Do you hear me? Because actually I thought that was meant. I forgot to put the microphone. Much better. So if m psi has positive root torsion, then it is not strongly fitted. Not strongly fitted. It might be weakly fittable or it might not. It might not be weakly fittable, this depends. But I don't want to go into details of this slide. And I would also not say what weakly and strongly means. Okay, so well, I repeat what the aim is. The aim is to find the generalization of these context structures here to higher dimension, so that we will get similar results as these ones. Okay. And before trying to describe what the generalization is, I will still look again at how to describe this in a more symmetric way. Where do I erase it? So both of these structures, both the Lutz tube and the root torsion, have a lot of symmetry, a lot of S1 symmetry. And we would use this S1 symmetry to try to generalize. So way to understand these two structures. So both, so the Lutz cube was given like this: cosine phi, cosine r dz plus r sine r d phi. And this has S1 symmetry